Patty's Calculus Videos, written and performed by me, Patty Leitner.
Part 3. Applications of the derivative. Section 3.9. Related rates.
Lesson 3. 2 further examples.
So the next example that we're going to look at is this one. Let's go ahead and read through it together, and again I'm going to have you pause the video at several points so that you can practice kind of pulling the information that you need out of the problem and putting it in the appropriate places in our 5 steps. And it's very important for you to practice it yourself because it's the only way to start to get a handle on how to do these. And just remember, these are tough problems. If you get stuck, it's okay. You're just barely learning how to do these. We've done 2 examples and this is only our 3rd, but you'll get a lot more practice as you work through your homework exercises. Okay, so let's read through this. This is a very traditional kind of calculus problem that you'll see in every calculus book. A conical tank, okay, that just means a tank that's in the shape of a cone. Do you notice that I have a cone here? Has a radius of 10 meters and a height of 30 meters. So this blue thing that's here is the overall size of my conical tank. And what the problem is telling me is that the height of this overall tank is 30 meters. So this is 30 meters. And the radius of this overall tank here is 10 meters. So this distance from here to here, the radius right here, maybe, yeah, I'll just leave it like that, is 10 meters. Okay, water pours into the tank. So here we have a pipe and water is coming into the tank. The water's green for some reason. Water pours into the tank at the rate of 20 meters cubed per minute. How fast is the water level rising at a certain instant in time, at the instant when the level has reached 6 meters? So here's the green water that is pouring into the tank, and so this, it sort of forms a conical shaped water down here. As the water builds up, it's going to be in the same shape of a cone. And so this is the water level at any time. So as water pours in, this level is going to be going up, 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 up. And so this is the green water that's down at the bottom of this conical tank. Well, let's think about it a little bit. First of all, we want to label the quantities that are varying in time. So let's try to figure out what quantities are discussed in the problem that vary in time. And let's see, they talk about water pouring into the tank at the rate of 20 cubic meters per minute. And they also talk about how fast is the water level rising at a certain instant in time. So pause the video for a moment, see if you can decide what quantities are changing in this problem that are discussed in the words of the problem, and see if you can write those then as functions of time. Okay, so now let's go ahead and look at step 1. We're asked to find the quantities, and remember those are all the quantities that are changing in time in our problem. So pause the video for a moment and see if you can pick those out. I'll give you a hint. There are really 3 important quantities that are functions of time in this problem. Okay, let's go ahead and talk about the quantities that are changing. I said there were 3 of them. Let's see if we can figure out what those 3 quantities are. We have this sort of conical shaped water that's down here in the tank, this green stuff, and as the water pours into the tank, this green cone is going to be increasing in size. Do you notice that the height of that green cone of water is going to be going up, and also the radius of the cone is going to be getting larger? So those are two quantities that change in the problem. So I'm going to call h the height of that green cone of water, and I will call r the radius of that green cone of water. Both of those are quantities that are changing in time. So I'm going to think of r as being a function of time. I don't know specifically what function, so I'll just write r of t. And h, the height, is a function of time. And again, I'll just write h as some unknown function of time. But there's another quantity that's changing. And you can probably maybe guess what that is at this point. It says water pours into the tank. So it's the amount of water that's pouring into the tank at the rate of 20 cubic, you notice this is in units of meters cubed per minute. So that's the rate that the volume of water is changing in time. Remember that this is a unit of volume, and that's because it is in meters cubed, or cubic meters. That's how much water is going in, so it's how much volume is going in per unit time, per minute. So the other thing that's really changing is the amount of green water that's in here, and by the amount of water, we really mean the volume of the water. And so that's also a function of time. As time goes on, there's more and more water, and so the volume should be something that's going up as time goes on. Okay, remember that the next thing we want to do is think about what rate we know. In other words, what rate do they tell me? And what rate do we want? What rate are they asking me to find? So pause the video again and see if you can pick out those two things and try to write them not only numerically, but also try to write them in terms of symbols, and think a little bit about their signs, whether they're going to be positive or negative rates of change. And then we'll go through it together. Okay, let's try this together. The rate we know, well, that's this number that we were just talking about. It's the 20 cubic meters per minute. And let's think about what that's the rate of change of. It says water is pouring into the tank at that rate. So that's the rate that I know, 20, I'm going to write it this way, meters cubed per minute. And let's go ahead and see if we can write it in symbols. Then we have to know what that is the rate of change of. It's the rate that the amount of water is changing in the tank. And remember, we said the amount of water is really the volume. You can also just look at the units and say, oh, the output units are units of volume. They're cubic meters. The input unit is a unit of time. And so it's got to be the rate of change of the volume, because meters cubed is volume, over time, because it's per minute, and that is a unit of time. So I'm going to write dV dt is equal to 20 cubic meters per minute. Now, is that the right sign? I put it's equal to positive 20 cubic meters per minute. That would indicate that I'm talking about a function v that is increasing in time. And is that true for this picture? Is the amount of water in the tank increasing as time goes on? Yes, it is. Water's pouring into the tank rather than leaking out of the tank, and so it should be a positive 20 cubic meters per minute. So you can put a plus sign there, or you can just leave it as a 20. Okay, the rate we want, let's see what they ask us to find. So they say how fast, so that's really asking what's the rate of change of the water level. So it says how fast is the water level rising at a certain instant. And remember, this instant is going to be something that we use at the very end of the problem when we plug in all of our known values. But the question here is, how fast is the water level rising? Well, which of our functions measures how high the water is? That's just the height of this green cone of water. So they're really asking how fast is h changing at a certain instant in time. So they want us to know how fast h is changing. H is a function of t, so really they want to know what's dh dt? How fast is the height changing with respect to time? So that's what we want to figure out. You can even put a little question mark there. That's what we're looking for. And we want it at a certain instant. It says at the instant, so I'll say when, just to make it a little bit shorter, the level has reached 6 meters. So when the water level has reached 6 meters, well, the water level is what we're calling h. So it's at the moment when h is equal to 6 meters. So water pours into the tank, the level rises, rises, rises. At a certain moment in time, h, the level of the water, will be exactly 6 meters, and we're asking how fast is the level changing at that instant in time. Okay, well, the next thing we have to do is to try to think about the relating equation. So we need something that relates these quantities we talked about together in an equation. The volume, and remember, it's really, we're looking at this green cone here, it's really the volume of a cone and the height of the cone and the radius of the cone. So again, this will be a formula from geometry that you may or may not remember, but try pausing the video, thinking about it, maybe thinking about how you would look it up if you don't know it, maybe in the back of your calculus textbook, or you might Google it if you don't know, and try to figure out what the relating equation is for the volume of a cone, its radius, and its height. Okay. Well, if you don't remember the formula from geometry, I'll just give it to you. It's V is equal to, it's really 1/3 pi is the way we usually write it, but I'm going to write it as pi over 3 r squared h. So that's just the formula for the volume of a right circular cone, which is what we have in this case. You may notice that there's something that's not very pleasant about this particular relating equation. And the thing that I don't like about this relating equation, look at what we ultimately want to connect together. We ultimately, after we differentiate, will want something that involves the rate we know, which is dv dt, and the rate we want, which is dh dt. This equation has a v in it, it has an h in it, so when we differentiate with respect to time, we'll expect a dv dt and a dh dt to pop out. But what else does it have in it? Unfortunately, it also has this r in it. It would be really nice if I had a relating equation that just had a v and an h in it, and I didn't have an r. So the question becomes, is there a way to rewrite this r in terms of h, so that I get something that's just h's on the right hand side, and I would have an equation that has only v and h in it. It would make it much nicer when I differentiate. I'll end up with something that has just dv dt, the rate that I'm given, and dh dt, the rate that I'm looking for in it. So you might think about it for a moment yourself. You can pause the video if you want to, but I will give you a little bit of a hint here before you pause the video. And this type of relating equation, how to figure this type out and get rid of one variable like this, comes up often. So the trick that I'm going to give you, the hint that I'm going to give you over here, is to think about similar triangles. And if you remember from geometry what the relationship is between a pair of similar triangles, you might go ahead and write down what those similar triangles are, write down the relationships between ratios of their sides, and see if you can rewrite r in terms of h, so that we'll eventually be able to substitute for this annoying r in terms of h. Try that for a moment, and then we'll go through it together. Well, let's go ahead and try this together. If you look at these cones, you could think about slicing the cone right along the plane that goes through the axis of the cone. And if you do that, you'll notice that there's really two triangles in here. There's this triangle that goes along with the whole tank, and then there's this triangle that goes along with the green cone of water. So that's what I tried to reproduce here. They're actually two right triangles because they are a slice of a right circular cone. And we also know something about the lengths of the sides of these right triangles. If you notice here, we said the overall tank is 30 meters high. So this side is 30 meters, and we said the overall tank has a radius of 10. So this length of this side here is equal to 10. And now concentrate on the little green triangle that's inside here. In fact, you can pull that triangle out separately. Sometimes it's easier to see that you have a pair of similar triangles if you pull those apart. So just ignore this triangle in here and think about the blue triangle that I have and compare it to the green triangle that's inside. They are a pair of similar triangles because the blue triangle and the green triangle have the same angle down here, and the right angle is certainly the same in both of those, and so this third angle must be the same in both of those. And you might remember this is the symbol we use for similar triangles, saying this big blue triangle is similar to this little green one, and because they have the same angles, they have the same shape, and so they're referred to as similar triangles. Well, if we look at the green triangle that's in here, this side is R, that's the radius of the green cone of water, and this side is H. So I have similar triangles, one of which has sides 10 and 30, one of which has sides R and H. Pause the video again and try to write down the fact that similar triangles have ratios of corresponding sides that are equal to each other. And then we'll go ahead and do it together. So let's go ahead and try to do that together now. Ratios of corresponding sides are equal in a pair of similar triangles. And you can set up the ratios in different ways as long as you make sure to always use corresponding sides. So we can say that the 10 that's in the big blue triangle is to the 30 that's in the big blue triangle in the same ratio that the R in the little green triangle is to the H in the little green triangle. So the radius of the big one to its height is the same as the radius of the little triangle to its height. And there are other ways that you can set up the correspondence. You could have also said 10 is to R, so 10 over R is equal to 30 over H. That's okay also. All right, so that's pretty good because that's something that involves a number, R and H. And remember what we were trying to do was to solve for R in terms of H so that we could replace R with something in terms of H. So I'm going to go ahead and try to solve for R in this equation. Let me cross multiply first. 10H would be equal to 30R. So it looks like if I solve that for R, I would get R is equal to 10H over 30, which would reduce to H over 3. So R is just equal to H over 3. So I'm going to kind of put this off to the side. All of this was just to rewrite R in terms of H. And now let's use that and plug that in place of the R that we saw right here. So that's what we will do next. I'm going to write V is equal to pi over 3. This was an R squared, so whatever I replace R with, that's going to have to be squared. And I'm going to replace it with H over 3 times H. Okay, that looks good. And now let's just go ahead and simplify a little bit. I get V is equal to pi over, the 3 squared becomes a 9. If I multiply by this other 3, I get 27 in the denominator. I have an H squared times an H, so it will be an H cubed. So now I have v purely in terms of h, which is nice because when we differentiate, we'll get something that involves dv dt, the thing that we know, and dh dt, the thing that we're looking for. Okay, what I'd like you to do next is to go ahead and differentiate with respect to time, as we did in our earlier examples, and then go ahead and try to do step 5 as well. Solve for the thing that you're looking for, dh dt, and then plug in everything that you know, including the fact that you want dv dt at the instant that h is equal to 6. So go ahead and try those last 2 steps on your own, then restart the tape and we'll go through it together. Okay, let's go ahead and go through this together. At this point, if you want, you can avoid rewriting all of these things as a function of time. I'm going to go ahead and write them as a function of time, again, just to remind you of which rules you need to use when. And you can always do it this way if you want to, but you may find that you can skip the step of writing v is v of t and h is h of t if you just think it firmly in your head and keep in mind that v is a function of time and h is a function of time. I'm going to do it again just one more time for us, and let's go ahead then. I'll write that down. V of t is equal to pi over 27 times, oops, I didn't give myself quite enough space there. So v of t is equal to pi over 27 times h of t quantity cubed. And remember that what we want to do now is to go ahead and try to take the derivative of both sides with respect to time. So I'm taking the derivative of this side with respect to time, and that's fine as long as I also take the derivative of the right side with respect to time, the same variable. Well, on the left side, as usual, we don't know what v of t is, so its derivative with respect to time, we'll just write that as v prime of t. And on the right side, remember that the pi over 27 is just a constant multiple, so that gets carried along. I get pi over 27. And when I take the derivative of h of t, the whole thing cubed, what rule will I need? Well, I have an inner function, namely h of t, and an outer function, it's really the t cubed function. So to find the derivative there, I will need the chain rule, just like in the earlier examples that we saw. So I take the derivative of the outer, that would be 3 times whatever I'm plugging in to 1 lower power to the second. So that's derivative of the outer. I evaluate it at the inner. Well, what's the inner function? It's h of t. And I multiply by the derivative of the inner, so times h prime of t. So that's just the chain rule to find the derivative of this portion, 3 times h of t squared times h prime of t. Now I'm going to go ahead and just rewrite that with our simpler notation. So with our simpler notation, v prime of t we usually write as dv dt. And on the right hand side, pi over 27 times 3, well, the 3 will divide into the 27 and leave me with a 9. So I get pi over 9. And instead of writing h of t squared, I'm just going to write h squared and suppress the of t. And instead of h prime, I will write dh dt. Now, as you get better at these problems and have more practice, what I was saying was that you can just go ahead and take the derivative with respect to time on both sides right here, as long as you firmly keep in mind that these are functions of t. That's very important for seeing where this factor of dh dt comes from. It comes from the chain rule and the fact that you really have an inner function of time and an outer function of t cubed. So you have a composition of two functions, and you need to do derivative of the outer evaluated at the inner times the derivative of the inner function. So that's where this extra dh dt is coming from. Okay, great. Now we should be able to try to solve for the thing that we want and plug everything in. Well, what were we asked to find? We were asked to find dH dt. So I want to isolate the dH dt here. Let me go ahead and do that. I'm going to put it on the left-hand side. dH dt will be equal to, and I'll divide both sides by pi over 9 times h squared, or another way to say it is that we're going to multiply both sides by the reciprocal of that. So when I divide this side by pi over 9h squared, or equivalently multiply by the reciprocal of those two factors, it looks like I will get 9 over pi. The h squared will end up down in the denominator, times dv dt. So that's just isolating the dH dt by dividing by this factor that's in front, or equivalently by multiplying both sides by the reciprocal. Now we can go ahead and try to plug in. So let's try to plug in for everything that we see. Looks like I have 9 over pi times, and h, do we know the value of h? Well, we wanted dH dt, but when did we want it? We wanted it as the water level's rising, rising, rising. We wanted it at the moment that the water level h was 6 meters. So in place of this h squared, I'm going to put 6 meters quantity squared. So I have 9 over pi times 6 meters squared times dV dt. That was the rate that we were given. That was the 20 cubic meters per minute. So in place of dV dt, I will put 20 cubic meters per minute. And now it's just a matter of simplifying all of that. 9 times 20 would be 180 over pi times, it looks like 36 meters squared. And then the units that are left here are meters cubed in the numerator and minutes in the denominator. And now it's just a matter of simplifying that. And I think I simplified it down, did I do that correctly? I believe so. 36 goes into 185 times, so I end up with 5 over pi. And let's look at the units for a moment and see what we're left with there. One of the meters in the numerator divides out into 2 of the meters in the denominator, and I'm left with just meters per minute as my units. And if you want to, you can plug it into a calculator. I think I did that to get an approximate value, and I got about 1.6 meters per minute. Now let's just take a moment to think about our answer and make sure it makes some kind of sense. First of all, dH dt came out to be something positive. So the rate of change of h with respect to time was positive. That would imply that h is increasing in time. The only way that dH dt, the slope of the tangent line, can be positive is if the curve hy equal h of t is something that's going up. And that certainly makes sense. Water is pouring into the tank, and so this cone of green water, its level is rising, h is growing. So that makes sense that the answer ends up being a positive value. What about the units? This is supposed to be the rate of change of the height, which is really a length, with respect to time. And meters would be a unit of length, of height in this case, and minutes is certainly a unit of time. So the units also look correct. Meters per minute, that makes sense for the rate that a height is changing in time. Okay, let's look at our last example. Okay, so let's go ahead and look at this last example together. Another related rates problem where they will give us a rate and they'll ask us to find a rate. It says your friend is running a marathon. So this is your friend right here, and she passes by you on a straight section of road towards the finish line. So this last part of the marathon is along a completely straight line, and here's the finishing flag over on the right. She's going at a 600 foot per minute pace. It says you're standing 20 feet from the road, so you're here and you're 20 feet away from this straight section of road, and you're taking a video of her with your phone. Well, in order to keep your phone pointed on your friend, you're going to have to change the angle that your phone is pointed at. Otherwise, she'll run right out of your frame. So the question is, to keep your phone pointed at her, how fast must you change the angle of the phone at the instant that she is 48 feet beyond the point on the road directly in front of you? Let's call the point on the road directly in front of you the point P. Okay, so that's sort of a long problem, but let's see if we can go ahead and think about it a little bit. What I'd like you to do is try to write down the quantities that are discussed in the problem that are changing in time. So see if you can think about what those are and try to assign them variables. You may pick different variables than I do, in which case you can switch if you want to have the same ones I do. But I want you to have some practice picking out what are the relevant quantities that are changing in time that are discussed in the problem. So take a moment to do that. Okay, well, we know that she's passing by you and going at 600 feet per minute. So they're telling me something about how fast she's running, and a way of interpreting that is it's the rate that her distance from this point P is changing. So we could go ahead and say, well, when I look at this problem, I can see that because she's running in this direction, her distance from point P is changing, and let me call that x. So x is a quantity that's changing in time. So I'm going to think of x as being one of my principal quantities that is changing in time. The other quantity that they talk about is how fast you have to change the angle of your phone. And why don't we measure the angle down from this line that's straight over to the roadway? So you could call that angle anything you want, but typically we'll call an angle like that theta. So we're really asking something about how that angle theta is changing. So theta is a function of time. As time increases, it looks like my theta is going to be increasing to be able to keep pointed at my friend. So theta is also a function of time. Okay, so great. We've discovered which quantities are changing in our problem. Now, this hasn't really come up in the earlier examples that we looked at, but just as important as the quantities that change in time are, also the quantities that do not change in time are important. And in this picture, there is a quantity that is fixed. In other words, that is constant. And can you see what that quantity is and what measurement, I guess, I could write down as a constant value, something that doesn't change during the problem? I want you to think about, well, for example, this side here is going to change, right? If theta is changing, then as she moves over, that distance between you, essentially, and your friend is going to be changing. But what distance is not changing? Notice it says that you are standing 20 feet from the road. So you're standing right here, the road's right here, neither of you are going anywhere, and so your distance to the road is a constant. Only when something is constant throughout the whole problem can we go ahead and write that down as a constant. So this distance right here is 20 feet, and it stays 20 feet throughout the whole process of her running by you and going to the finish line. So it's okay to mark this with a 20. We couldn't mark this with any value such as 48 or something like that because it's changing during the course of the problem. Theta is changing during the course of the problem, but this is staying fixed at 20. So just notice that the constants are as important as the variables in our picture. Okay, now what I'd like you to do is pause the video and think about the rate that you know and the rate that you want. So the rate that you're given, write that down numerically and also in terms of symbols, and then write down the rate that you want in terms of symbols, and be sure to mark down in brackets at what moment in time you want that rate. Then we'll go through it together. Okay, the rate that we know, the one that we're given, well, I can see right here I have a feet per minute, which clues me into that being a rate. It says she passes by you on a straight road at the rate of 600 feet per minute. Well, what's that the rate of change of? Well, if she's moving at 600 feet per minute in this direction, that means that x, her distance from the point P, is changing at 600 feet per minute. So the rate that we know is the 600 feet per minute. And what is that the rate of change of? Well, it's how fast x, her distance from P, is changing. So it's the rate that x is changing in time. In other words, it's equal to dx dt. Is that correct to make dx dt a positive rate of change? Well, x is going to be something that's increasing, and so remember we said that an increasing function has a derivative that is positive. So dx dt should be something that is positive, so that's okay. What about the rate that we want? Well, it says down here that to keep pace, or to keep your phone pointed at her, how fast, in other words, at what rate, must you change the angle of the phone? At a certain instant in time, at the instant when she's 48 feet beyond the point on the road directly in front of you, in other words, beyond the point that we labeled P. So how fast, that's asking at what rate, so that's the rate we want, must you change the angle of your phone? In other words, how fast is theta changing? How fast do you have to keep changing this angle of your phone? So how would I write that in symbols? Well, it's just the rate that the angle, theta, is changing in time. So d theta dt. And notice we want it at the instant when, well, it's at the instant that she is 48 feet beyond the point P. So it's at the instant that she's 48 feet away from P, it would be the instant then that x, that's her distance from P, is 48. So at the instant in time when x equals 48 feet. Okay, now I want you to pause the video again and see if you can come up with the relating equation. And notice that we really do have a little right triangle in here. If we're talking about your distance from the roadway, we always mean the shortest distance, and that will be the distance of the line that comes in at a right angle to this other line. So keep in mind that you really do have a little right triangle in here. But also keep in mind that the Pythagorean theorem will not be terribly helpful in this case, because what does the Pythagorean theorem say? It says how the sides of the triangle are related to the hypotenuse of the triangle. What we would really like to do is to relate x and theta together in an equation. So see if you can think about how to relate x and this angle theta together in an equation. Okay, let's try this together. I've got a right triangle, and I know that this side is 20, this side is x, and I have an angle of theta. So if you look at it from the point of view of this angle theta, notice that x is the side opposite it. I'm going to write that in red. X equals the opposite side to the angle theta, and 20 is the side next to theta. So in trigonometry, it's what we call the adjacent side. So let's go ahead and think about which of the trig functions of theta would involve the opposite side and the adjacent side. Remember that tangent of an angle is equal to the opposite side over the adjacent side. The side opposite the angle over the side adjacent to the angle. So what would we have here? We would have tangent theta is equal to, well, the opposite side is what we're calling x, and the adjacent side is fixed, it's a constant, it's always equal to 20. So tangent of theta is equal to x over 20, and that's our relating equation in this case. So let me go ahead and write that down. We would have tangent theta equals x over 20. I'm going to write it this way as 1/20 times x. It's just a little nicer way to write it, so we write it as a constant multiple of x. And remember again that we could go ahead and put those of t's in. Remember that theta is really a function of time, so I could think of it as tangent of theta of t equals 1/20th times an x, as we said, is a function of time, so I could write that as x of t. So 1/20th times x of t. All right, what I want you to do next is to do step 4 and try to differentiate with respect to time on both sides of this equation. And remember to use all the proper rules that we talked about that are needed for differentiating these particular functions. And then try to clean it up and rewrite things without the of t's and the of, and also without the theta primes and the x primes of t's. Rewrite those as d theta dt and dx dt. And then we'll go ahead and go through it together. Okay, so let's try differentiating. So I'm going to be taking the derivative with respect to t on the left side, and that's fine as long as I also take the derivative with respect to t on the right side. The left side equals the right. The derivative with respect to t of the left should equal the derivative with respect to t of the right. So now it's a matter of finding those derivatives. So let's see if we can do that. Find the derivative on the left side. And you have to think about, do I need any special rules of differentiation? Well, I've got tangent of theta of t. In other words, there's an inner function, theta of t, inside the tangent function. It's a composition of two functions. What rule do I need to find the derivative of a composition? I need the chain rule. So let's go ahead and use the chain rule on the left-hand side. All right. Remember, I start by taking the derivative of the outer function. So I start by taking derivative of the tangent t function. Derivative of tangent, remember, is equal to a secant squared. So I will get a secant squared for the derivative of my outer function. So chain rule says take derivative of the outer, and where do I evaluate that? I evaluate it at the inner function, so I have to put a theta of t inside here. And then I'm supposed to still multiply that by the derivative of the inner. Derivative of theta of t, since we don't know what function that is, the best I can do is write theta prime of t. So all of this is just applying the chain rule to the left side. Derivative of the outer is secant squared, evaluated at the inner, theta of t times theta prime of t. On the right-hand side, I do have a constant multiple of 1/20th. So that just gets carried along. And then I take the derivative of x of t. I don't really need any special rules there. Of t is not a function I know, so the best I can do is say 1/20th times x prime of t. Let's go ahead and just write this in the compressed notation as I asked you to do, or to try to do. So I'm going to write it as secant squared. Instead of theta of t, I'm just going to go back to theta. And instead of theta prime of t, I can write that as d theta dt. It's just a little easier to handle. And that will be equal to 1/20 times x prime of t. In the alternate notation is just dx dt. Okay, great. So let's remember what we were looking for, because in the next step we're going to try to solve for the thing we were looking for. And the thing that I wanted was d theta dt. So I need to try to isolate the d theta dt that's over here. Well, how do I isolate d theta dt? I guess I could divide both sides by secant squared theta, but I'm remembering in my head that secant theta is the same as 1/cosine theta. So I'm going to rewrite this before I isolate. I'm going to write the secant squared as 1/cosine squared theta. So remember, secant theta is just 1/cosine. So secant squared of theta would be 1/cosine squared theta equals 1/20th. I think it'll just make it easier to try to isolate this factor of d theta dt that's on the left-hand side. So to get d theta dt by itself, I could multiply both sides by cosine squared theta. So let me do that. So d theta dt, that's the thing that we want, would be equal to 1/20th times, and when I invert and multiply, I get cosine squared of theta, I'm multiplying both sides by that, times dx dt. So now I've isolated the rate that I want. And now we want to go ahead and try to start to plug everything in. So we want a d theta dt at the instant when x is equal to 48 feet. Okay, well, let's think about that for a moment. I don't even see an x anywhere in this right-hand side. I do know the value of dx dt. That's the rate that she's running, the 600 feet per minute. Well, let's plug in what we know, and we'll try to figure out how to do everything else. So let's see, I'm going to go ahead and try to plug in everything that I do know. I'm going to do that. Let's see, I'm running out of room, so I'm going to actually move this slide up a little bit so that we can complete this. And just ignore these numbers that are down in the bottom corners of my original slide. Those are just my overhead slide numbers. So let's go ahead. One thing I do want to mention is I have this 1/20 here, and the 20 came from the 20 feet. Now that I'm plugging things in, since I want to include my units, I'm just going to put down the fact that that constant of 20 really has a unit associated with it, so it's really 1/20 feet if I want to include the units. Now cosine theta, I don't know what that is at the moment in time that she's 48 feet beyond the point P. So I'm just going to leave that as cosine of theta, but I am going to write it without this shorthand notation. Cosine squared theta means I take whatever cosine of theta is and I square it. We'll try to figure out what that is at the instant that she's at 48 feet from point P. But dx dt I know, that's the rate that she's running, that's the 600, and again I'm going to include the units, feet per minute. Well, how the heck am I going to figure out what this cosine of theta is? I do know that, I'm redrawing my little triangle down here, here's my theta. I do know that this side is always 20 feet. And I know that I want cosine of theta at the instant when this side is 48 feet. I want it at the instant when x is equal to 48. So the question becomes, can I figure out what cosine of theta is at that instant in time? And you might remember from your right triangle trigonometry, cosine of theta is the side that's adjacent to theta divided by the hypotenuse. Well, I actually know the side that's adjacent to theta. That's this side. So that's 20 feet. I don't know the hypotenuse, but could I figure that out? Sure, I could figure that out. Let's call that z, for example. And now the Pythagorean theorem is helpful. I know that z squared is equal to this side squared, which is 20 squared, plus this side squared, which is 48 squared. And so I get z squared is equal to 400 plus 48 squared turns out to be 2304. So if you add these together, I'm cheating and looking at my notes over on the side, I get 2704. It would really be in units of feet squared, because this is 20 feet squared plus 48 feet squared. So z, if I take the square root of both sides, this turns out very conveniently to be a perfect square. It turns out to be 52, and the square root of feet squared would just be feet. So z turns out at that moment in time to be something I can calculate, and it's 52 feet. So if we go back down here to cosine of theta, we said it's the adjacent over the hypotenuse. That's 20 feet over, and now we figured out that the hypotenuse at that instant in time is 52 feet. And if you want to, you can go ahead and reduce this. The top and bottom are both divisible by 4, so I would end up with 5 divided by 4 into this is 13. And notice the units actually cancel out completely. Cosine of theta is just the number 5/13. Well, great. what I've done is I figured out what cosine of theta is, and that was the last thing I needed to figure out at the instant when x is equal to 48. So all of this stuff we can think of as being done on a piece of scratch paper, maybe that's on the side, but it was necessary in order to figure out what the value of this cosine of theta was. So all of this was to figure out what cosine of theta is at that particular instant in time, at the instant that x is 48. Okay, so I'm going to go ahead and plug that in. And cosine of theta is the pure number, no units, 5 over 13 squared, and then I have times 600 feet per minute. Now it's just a matter of trying to simplify all of that. So I'm going to have a 25 when I do the 5 squared in the numerator. 13 is going to be 169 when I square it. And I multiply all of this stuff out. I ended up getting the following for the exact answer, 750. It's all divided by 169. And you notice that the feet drop out because I have 20 feet here and I have the feet in the 600 feet per minute there. So I end up with per minute and no units in the top at all. Okay, that's kind of weird. But if you think about it, remember we're working in units of radians. So what we're saying is that d theta dt, the rate that the angle is changing in time, is 750 over 169, and we're really working in radians. And remember that radians are just a pure number, meaning that they don't really have any units attached to them. It's part of the reason that we like to work in radians. So radians is really a pure number, so you're saying it's this pure number per minute, but it usually feels more comfortable to go ahead and put radians per minute. So we're really saying that it's changing at this many radians per minute. If you want to go ahead and get a decimal approximation for that, it turns out to be about 4.44 radians per minute. And you can even convert that to degrees. To convert radians to degrees, you just divide by 180 degrees per radian. And so that turns out to be about, I think I converted it into degrees per second. It just seemed a little bit better. So I multiplied by 180 degrees per radian over radians, and then I converted it from per minute to per second by dividing by 60 seconds in each minute, and I got 4.24 degrees per second. That's just a little more useful in terms of actually visualizing what's happening. So what's that saying? It's saying that if she's running at a constant rate of 600 feet per minute towards the finish line, you have to keep moving the angle of your phone to track her at the rate of about 4 degrees per second at the instant that she is 48 feet away from this point P. Okay, well, as you proceed and do examples in your exercises, just remember that each one of these problems is slightly different. They are all challenging, and each one we can break down into these 5 steps. Always try to figure out the quantities that are described in the problem that are changing in time. Try to figure out the rate that you know, the one they give you, and the rate that you want, the one that they ask you to find. The relating equation can be tricky, and it depends on each problem how difficult it's going to be to find that relating equation. But once you find it, we differentiate with respect to t on both sides, and then we plug in all the information that we are given. And sometimes we have to do a little bit of extra work in order to figure out certain unknown quantities at a particular instant in time.